What core knowledge does a signage factory technician need to master in order to skillfully operate 3D printing equipment for sign production? Today, we'll focus on 3 key sections: model design, critical parameters, and assembly accuracy, and explain those important parameters and concepts in language that signage factories can easily understand. First, the modeling stage. 3D printing first requires a model. Just like when we use a laser cutter or a CNC engraving machine without a drawing, nothing can start. Laser machines use 2D files, mainly CAD and CorelDRAW. 3D printing, however, uses 3D model files, most commonly STL files. Model sources. One method is self-building using modeling software to create the desired shapes. This is suitable for more complex or customized letters and processes in the advertising industry. The most commonly used modeling software is SolidWorks and Fusion 360. Since many technicians in small sign shops only know how to use 2D software in order to reduce the learning barrier, SASM 3D has specially developed a 2D to 3D generation software. By uploading a 2D drawing or manually entering standard text, and then adjusting a few lettering parameters: letter shell thickness, height, base plate thickness, and the step position for holding the acrylic, the system can directly generate 7 common channel letter manufacturing processes. FDM fused deposition modeling. FDM printer is essentially a moving motor system equipped with a high-temperature extrusion head. The extrusion head heats up to around 300 C. Under high temperature, the filament turns into a liquid, follows the motion of the motors, and is extruded out, then deposited onto the heated bed, where it cools and solidifies into printed objects of different shapes. Next, following this basic principle, we will go through the fundamental concepts one by one and make each of them clear. Second, basic concepts that a sign factory needs to understand: nozzle diameter, layer height, and layer thickness. The nozzle diameter refers to the outlet hole size of the print head. At present, the commonly used nozzle sizes on the market are mainly 0.4 mm and 0.6 mm, and the corresponding common layer heights are 0.2 mm and 0.3 mm, respectively. The nozzle diameter and the layer height together determine the deposition thickness of each layer of material on the heated bed, thereby directly affecting printing accuracy and forming efficiency. In the actual application of channel letters, unless there are extremely high requirements for surface texture, for example, results close to a precision craftsmanship level, and post-processing such as sanding and spray painting is required, a 0.6 mm nozzle can already meet the needs in the vast majority of scenarios. Its forming precision not only covers the requirements of traditional bending letter processes, but also provides higher printing efficiency. For applications pursuing a finer surface finish and targeting high-value precision letters, a smaller diameter nozzle such as 0.4 mm or even 0.2 mm can be selected. However, it should be noted that as the nozzle diameter decreases, the extrusion volume per unit time will drop significantly, and the printing time will also increase substantially. Layer height and layer thickness. When the plastic filament is deposited onto the heated bed, due to gravity it spreads slightly to both sides, and in the side view it forms a rectangular shape. The width is approximately 1.2 times the nozzle diameter, but for convenient calculation we treat it as 1:1. The excess portion will be compensated by the software. The default line width is 0.6 mm, and the layer thickness, that is, the layer height, is approximately half of the diameter, with a default of 0.3 mm. In the advertising industry, material selection is not arbitrary, but is determined by the forming process itself. Because the principle of FDM is high temperature melting and low temperature forming, shrinkage is unavoidable and will affect forming quality. The materials commonly used in the advertising industry mainly include 3 types of filament: PLA, PETG, and ASA. PLA is a recyclable bio-based material. Simply put, it is a secondary processed product made from corn stalks. This material is environmentally friendly and has low shrinkage, so the printing quality is very high. However, its advantage is also its disadvantage. It is recyclable and naturally degradable, very eco-friendly, but not very suitable for providing long-term warranty in the advertising industry. Essentially, it is the same kind of naturally degradable recycled plastic as the coffee straws you often use. PETG. PETG material is often used in advertising boards. Because its raw pellets are transparent, light diffusing powder can be added to create an acrylic-like frosted appearance, which unlocks many application scenarios for channel letters. However, because the carbon chains of plastic polymers are easily damaged by ultraviolet light, from a polymer theory perspective, it is not very suitable for outdoor use. SA. From the standpoint of polymer chemical principles, this material is the only filament that possesses UV resistance and can be adapted for long-term outdoor use. Since PETG and SA both belong to engineering plastics, and the nature of engineering plastics is to absorb moisture, dehumidification is required before printing and also during printing. In addition, because plastics shrink and generate internal stress during high and low temperature cycling in the forming process, a heated chamber is required during printing to ensure that deformation of the printed part is not too large, and also to make production and signage manufacturing repeatable and reproducible. Based on the principles of FDM 3D printing, we now return to the basic parameters of print settings. Printing temperature. Here it is divided into nozzle temperature and heated bed temperature. Nozzle temperature. This is the temperature used to melt the filament. Different materials have different melting points and must be set accordingly. For example, PETG 220 to 250 degrees Celsius, SA 240 to 280 degrees Celsius. If the temperature is incorrect, either the print will not bond firmly, or there will be stringing everywhere. Heated bed temperature. This is the temperature of the heated printing platform. Its main purpose is to allow the first layer to firmly adhere to the platform and prevent the corners from warping. Different materials also require different bed temperatures, and a SA requires a higher bed temperature than PETG. Printing speed and volumetric flow rate. What we usually call printing speed is the travel speed of the printhead driven by the motors. However, real production efficiency depends on the volumetric flow rate. As mentioned earlier, the deposited filament forms a rectangular shape inside view. As the motors move, it is stretched into a rectangular solid. The volume produced per unit time is the volumetric flow rate. Multiply this volume by the material density to obtain the filament weight, and when converted into grams, it directly becomes the production cost of the signage. Maximum volumetric flow rate. This refers to the maximum amount of filament that the nozzle can extrude per unit time. In other words, the extrusion head's maximum output. This volumetric limit is also constrained by the maximum volume of filament that can be melted inside the extruder's heated throat. Flow ratio. This controls the actual amount of filament extruded by the printhead. It can be understood as controlling how much material the nozzle pushes out. Too much extrusion causes material buildup, while too little extrusion results in gaps. Seams. 3D printing is built layer by layer, and the connection point where each layer starts and ends is the seam. Normally, we place seams at less noticeable corners. However, if the shape is circular such as the letter O, a visible seam is unavoidable, and post-processing, such as sanding, may be required to deal with it. Third, the assembly stage. After printing is finished, can the product be installed and shipped right away? Not necessarily. Sometimes we find that a letter designed to be 50 centimeters ends up being 49.5 centimeters after printing. Or acrylic panels that were cut exactly to size simply cannot be installed. The root cause of these issues lies in the thermal shrinkage characteristics of the printing filament. During printing, the filament is in a molten, liquid state. As it cools down and solidifies, slight shrinkage is unavoidable. This easily leads to problems such as the letter shell and the acrylic not fitting properly, or male and female parts failing to align during assembly. This issue is especially noticeable with ASA filament designed for outdoor use and UV resistance, as its shrinkage is more pronounced than that of standard materials. To solve this problem, there are two approaches. First, use a printer with a heated chamber. The heated chamber keeps the printing environment warm, allowing the filament to cool down slowly. When cooling becomes more uniform, shrinkage is more consistent, and issues such as warping and deformation during printing can be effectively reduced. Second, for ASA parts used outdoors, there is one essential step that cannot be skipped: stress relief. During 3D printing, the material goes through heating, melting, cooling, solidifying, and layer-by-layer stacking. Because temperature changes are uneven and layers restrict each other, an internal pulling force is formed inside the printed part. This force is called stress. Stress is the main cause of warping, cracking, and layer separation after printing. This effect is more obvious in ASA filament. Therefore, once an ASA print is completed, stress relief is necessary. Specific steps: first, pre-assemble the printed parts and acrylic sheet, then place them in a constant temperature environment 60-70 C and let them stand for at least 2 hours to allow the internal stress to dissipate slowly. All of these key points form the core knowledge that professionals in the advertising signage industry need to truly master 3D printing technology. Once you fully understand them, you'll be able to use 3D printing with confidence to produce signage, and quickly grow from a beginner into a skilled, hands-on practitioner.